Welcome to this NAPIT webinar on EV charging Amendment 1. My name is Paul Chaffers. I'm the Technical Events Manager at NAPIT. And joining me today is Conor Charnley from Garo. Garo are one of the major EV charge point manufacturers, one of the leading brands out there. And I'm going to hand over to Conor to do a short intro.
Thanks very much, Paul. Yes, my name's Conor Charnley. I work for Garo as the UK sales manager. Garo is an 80-year-old distribution company manufacturing many products through RCDs, MCBs, and CAA, among others. And for the last 10 years, we've been focused very heavily on the AC and DC charge points for this new evolution of the electrical market.
Okay, thanks, Conor. So we'll be doing questions at the end. I'm going to be covering all the regulations and BS 7671 stuff, and Conor's here from a charge point manufacturer's point of view. So between us, we should be able to deal with most things. So the amendment was published in February. So it's BS 7671 Amendment 1 2020. It's available free to view on the IET's website. It's a standalone update to section 722, so it's just only affects EV charging. So when we talk about Amendment 1, it doesn't affect any of the other regs, just EV charging. You can implement that straight away because there are some solutions in there, and we're going to be talking about these this morning. However, if you're not quite up to grips with it, you've got until the 31st of July where you must comply. So there are a lot of little minor editorial tweaks here and there, bits and pieces being moved, and that happens with most amendments. But we're going to be looking and focusing on the main things that will affect the installations of charge points. And the first one here is maximum demand and diversity. Now, we used to have to look at the full rated current of the EV charging device, look at our maximum demand and see if there was enough spare capacity to install our charger. Okay, we couldn't use diversity if we had multiple points. So it was quite restrictive, really. And with, the government wanting to push these charge points out there and everybody wanting to go green, it was quite unhelpful. So the new regulation in the amendment, written at the bottom there, 722.311.201, it allows for load curtailment, including load reduction or disconnection. It can be either automatically or manually, and it must be taken into account when determining the maximum demand of an installation. So it gives us some solutions. The removal of the requirement to consider EV charging points at the maximum rated current removes installation barriers, as I've previously said. It takes advantages of the manufacturer's load management solution. So I'm just going to hand over to Conor, who's going to talk about their dynamic load management system.
Thanks, Paul. Yeah, we have a great solution for dynamic load management. With our solution in a domestic environment, we would install a meter at the head of the application, which would communicate back to the charge point on a built-in cable. It's a Modbus communication. From that point, the charge point can see exactly the total load of the home. So it'll take into consideration showers, cookers, lighting circuits, and as the circuit rises or the circuits rise within the home, the charge point will then automatically reduce itself. It won't automatically turn off, but it will reduce itself down to a safe load. Now, the great thing is with that system or that type of system that we've developed, as homes change and move away from diesel or petrol cars to have two EVs, we can then add a second EV point in there as well. And we can load manage up to 32 charge points. And I appreciate that won't be on the standard home. But when we look at the domestic the commercial markets and what's happening there, there's maybe 25, 30. We've done some applications with 100 charge points on an apartment block or on a large car parking space. We can then load manage circuits up to maybe 600 amps 3-phase and give a solution where it will automatically change the load as the load in the building changes. It's a massive benefit, especially with the fact that we've got limited supply in our buildings at the moment.
Okay, that's fantastic, Conor. Really, and that's all automatic. The customer doesn't have to change anything, get involved at all. It just happens automatically. Yes.
Yeah, providing the install set up correctly in terms of on the day of setup, yes, that will be an automatic solution. As car 1 connects, it's 32 amps. Let's say we've got it set for a 3-phase 100 amp scenario. As up to the 4th car connects, load management will then automatically kick in and reduce the load across the cluster. You can also introduce smart charging as well, Paul.
Okay.
Now, what that would allow you to do is have a management system in the back end, and you can then set up more sophisticated criteria around load management. But with DLM, it is very much the charge point's brain linked to a meter, and it will automatically divide the load that we specify. And there's some real unique features within our charge points when you get to configuration.
That's fantastic. Excellent. Okay, moving on. So we're talking about these loading situations. Now, this next few slides have got nothing to do with Amendment 1. This is just some information that NAPIT wanted to bring to you regarding loading and consumer units. Distribution boards and consumer unit assemblies, they're rated by the manufacturer after applying an assumed loading diversity factor, which is known as the rated diversity factor, the RDF. Okay, and what it does, it considers what can be continually and simultaneously loaded. And we need to apply this because EV chargers are a constant load. So unlike a shower or something that goes on 5 minutes later, it's off, there's no real concern. An EV charger could be on for quite some time. Okay, so we need to look at the RDF factors. Now, you've probably never noticed this, or you may have noticed this, but if you look in consumer unit instructions, quite often you'll see some little tables and charts. Next time you're doing a board change, have a look and see if you can find some advice on RDF. This table here is from the product standards and actual from Beamer. If you look at the Beamer documents, they've got all this stuff readily available. This table is from table 9.1 from our on-site solutions publication. We've got a complete section on EV charging within that publication, so have a look at that if you've got time. Now, let's look at, say, a 10-way board. Most consumer units these days are of, at least 10 ways. If you see there, you've got a 0.5 factor. So what the manufacturers have done there is they are assuming that each MCB in that board, each circuit breaker in that board is only working at 50% loading. Okay, that's the diversity that they've allowed for it. So we've got an issue there, because if we've got most of these cars have a 7.4 kilowatt inverter in them, so they'll be looking for a 32 amp charge. If we've got 32 amp charge continuously loaded circuit breaker, and we were to apply this factor, we would need to double the circuit breaker for it to work correctly, because circuit breakers, as you know, they have a bimetallic strip in there. It works on temperature, and when it gets to a certain temperature, it feels there's an overload, it switches off. If the heat can't escape because of this constant loading, the circuit breaker may not hold the charge. So taking this loading factor into consideration, we would need to put double the circuit breaker, but they don't do a 64 amps. We'd have to have a 63 amp circuit breaker in there, and of course that causes a problem because we would now need larger conductors in our circuit. So we need to think about this from the design stage, and what you really need to do is have a look at the distribution board and see what different ways you can configure that to make sure that you've not got the EV charging next to a circuit that is continuously loaded, and then you won't have any simultaneously loading effects on that EV charge point. You can talk to the manufacturer of the consumer unit. They may be able to tell you about other configurations that you can use. Again, we've covered this in depth in the on-site solutions. Okay, so the next big topic is with regards to PME earthing systems. So Regulation 722-411-41 introduces two new indents, 4 and 5, which provides alternative solutions for charging installations using PME earthing systems when you're charging outside. The existing installation options 1, 2 and 3, they're still available. They've been slightly modified, but the principles are the same. Many contractors doing EV charging found those conditions hard to meet, as summarised below. So the first requirement, or first method, concerns charging points forming part of a three-phase installation that's also supplying non-vehicle charging loads. In the event of a fault in the pen conductor, what we're trying to achieve here is that we don't get 70 volts touch voltage. So what this requirement is looking for is a balanced three-phase installation where there's not much current flowing in the neutral. Okay, so it's quite hard to meet, because as we design installations, if it's a new build, you're going to have all of the loading considerations mapped out for the design. You're going to know what the different where the different loads are. You're going to be able to balance them up. You're going to be able to get the phases fairly balanced. But in theory, what happens is, as the installation goes on, loads change, different circuits get moved around, the balances become unphased, they're not balanced anymore, the phases, and then you get situations where you have single phase loads kicking in and out, causing imbalance in the system, and therefore you have current flowing in the neutral, and this is what can cause the voltage to rise above 70 volts if we have a lost pen conductor. So it's quite hard to achieve, but in theory it can be met. Second option was to install an auxiliary earth electrode in parallel with the MET. So you've got a TNCS supply, you're going to put an additional earth electrode in to try and tie down the touch voltage to under 70 volts, and the only way you could achieve that was by meeting this formula here. Okay, so the RAEV, that's your new electrode and the conductor connecting it to the MET, and then we've got 70 volts there and Cmax. We have to use the Cmax formula because the voltage is allowed to be distributed with a plus or minus allowance. It's allowed up to 10%. So if we add 10% to our 230, we get 253 or whatever it is. So what we need to do is we need to use a Cmax factor of 1.1. So it's 70 times Cmax times U0, which is 230, and we divide that by the bottom. Now, I've explained all the stuff on the right hand side. The INST is the installation's maximum demand plus the EV charging load. Okay, so it looks complicated, but it's a fairly easy formula to do. Now, when we run some demonstrations of this, when we were putting the on-site solutions together, we found that in order to achieve the 70 volts touch fault conditions, you needed an RAEV fairly low, sort of 1 or 2 ohms, so very unachievable in most cases. So option 3 concerns a device which disconnects the charge point if it sees a voltage between the CPC of the charge point and true earth. If that rises above 70 volts, it disconnects. Now, to our knowledge, these devices for this ident 3 is not available, but there's nothing to stop manufacturers from producing that, so it is a third option. Okay, so out of the 3 options, it was fairly hard to comply, and therefore Amendment 1 produces some further options. Prior to that, the contractors out there would struggle to meet one of those 3, so they would look at a TT arrangement. Okay, so we have a picture here. You can see we've got the TNCS at the service head there, and the circuit coming out to the EV charge point is using the TNCS, and then it's separated at the plastic box there just below the charge point, and a dedicated earth electrode is used for the EV point. So that's absolutely fine. That's a TT arrangement, no problem. We're not going to get any problems from that PME system. However, Amendment 1 has introduced a note, and the new note, Note 6, it it says that creating a TT system may not be suitable. It may not be because of the buried metalwork. Okay, so it is an issue that we're talking about at committee level, and what we're talking about is voltage transfer. So let's have a little look at that. If we imagine you've got PME supplied to the building over there on the right hand side, and you've got the service pipes under the ground going into that property. When they're inside that property, if they're metallic, they're more than likely going to be bonded, okay, to the PME, the MET. So if there is an open circuit fault, there's a lost pane conductor, and the pipework within the installation rises in potential. Within that potential, we have our equipotential zone, so that limits the effects. However, the pipework underground there is also going to rise in potential. And now we're going to get a situation where we could have voltage transfer. And if you have a look at that, where we've got that dotted line there, we could have voltage transfer from the pipe under fault conditions across to that electrode, and it could come back up to the charge point and onto the chassis of the car. So this is what we're talking about with TT installations. We need to be concerned that we're going to have a suitable separation distance from any buried metalwork. And I know you're all going to be thinking that, you know, where are these pipes underground? Are we going to need CAT scanners, etc., etc.? Well, these are all things that need to be considered. Okay, so a TT system's absolutely fine, but you need to consider this. So, new indents now. The first one, indent 4, protection against electric shock in a single phase installation is provided by a device which electrically disconnects the vehicle from the live conductors of the supply and from the protective earth in accordance with regulation 543.33101 in 2. That regulation there is because we're disconnecting the protective earth, okay, which is something we don't often do. So that regulation requires if you're disconnecting the earth, it doesn't get disconnected prior to the live conductors, and when it's reintroduced before or at the same time as the live conductors. Okay, so that's what that regulation is concerning there. Okay, now this device, it doesn't have to disconnect up to 4 seconds, but it must disconnect within 5 seconds. Okay, if it sees the voltage between the line and neutral conductors fall outside of those voltage bands there, so 207 to 253. Okay, so this device needs to be set to operate if the voltage goes outside of those parameters. One of the characteristics of losing a PEN conductor is the voltage dips and it flies all over the place. So if it goes flying up or down, the device will see that. After 4 seconds, it needs to disconnect within the 5 seconds. Okay. It must also provide isolation. So it needs to be selected in accordance with table 537.4. So if you look at that table, it gives you all the devices that meets the requirements for isolation. And a lot of these charge points have contactors in there to deal with that isolation. Okay, so that's a great solution. If we get any kit, whether it's built into the charge point or whether it's an external bit of kit, if it can meet that requirement, then we don't have to worry about the TNCS. We can use TNCS, no problem, because we've got a device that under full conditions will disconnect the problem. The next indent, and the last one, was introduced really to allow EV manufacturers some flexibility to design different solutions. So the first one is it's very exact. You must measure between line and neutral, and it must do this, 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 and this. This one allows manufacturers to build safety into their equipment as long as it's no less safe than the previous conditions that we've just talked about. So again, the amendment is providing flexibility for this future growth that's happening with EV charging, and we're going to see these new solutions come out. So that's a snapshot of the 5 choices. We've got the first 1, 2, 3, which were existing. We've got the new one, which is 4, which is a device that will measure between line and neutral. And we've got this last one that is an alternative device that's no less safe. It also has to provide isolation in accordance with table 537.4. Not very easy for me to say today. Okay, there is a note with this, note 5, and it basically goes along the lines that the regs doesn't deal with the construction of electrical equipment. Okay, so therefore it's your responsibility to make sure that you've got the right equipment for the job, and you need to check with the manufacturer and say, is your equipment safe for installation on PME? And if they've got some sort of declaration of conformity or some sort of statement that says their equipment meets condition 1, 2, 3, 4, or 5, or whichever one of those previous points we talked about, great. And we would recommend that you keep that declaration of conformity with your design stuff, or even with the certificate, so that you can prove at a later date, if there is any sort of further backlash, that you've installed the equipment and you've adhered to this note and checked that that the equipment does meet the correct standards. Okay, so next up we're going to look at RCDs. Okay, so unless you're using the protective measure of electrical separation, you need a 30 milliamp RCD for each charging socket. Okay, and except where provided by the EV charging equipment, the protection against DC fault current shall be provided by a type B RCD or a type A or F RCD in conjunction with residual direct current detecting device, the RDCDD. So the new thing here is the type F and also the RDCDD. That was new to these regulations. Okay, now in the previous webinar that I done on the 18th edition consumer units, which you can view over on the NAPIT forum, I went into great depth with RCDs, so I'm going to sort of try and skim over it a little bit here now and go over the basics. But if you want to have a closer look at RCDs, refer back to the 18th edition consumer unit webinar that we done. Okay, so these are the different types. Okay, and the general requirements of the regs tells us that there's different RCDs that work different with DC components and frequencies, and you must choose the correct one. So the type AC is the basic one that we've had for years and years and years, and they're starting to be replaced now with type A's and F's and B's. And a type A device will work up to 6 milliamps DC leakage, and a type F will be 10 milliamps, and a type B does everything. So that's the kind of hierarchy of them. The type B is the best and the type AC is the worst. Okay, if Conor's still there, I'm just going to bring Conor in. Conor, which RCD does Garo recommend using with your devices?
Garo manufactures both type A and type B RCDs, but with our devices, all our AC charge points that we manufacture for the UK market have DC leakage monitoring built in. So you would have to use, or you could use, a type A RCD for those. Okay,
excellent. So basically what we're saying then, if the DC leakage from the batteries, car, whatever, starts to cross into the, into the circuit, the type AC RCD will work fine up to 6 milliamps. Okay, if it goes above 6 milliamps, we know from the product standards that the type A RCD is no longer any good. So now we're relying on the DC monitoring in your unit to shut the circuit down. Is that how I understand that correctly?
Yeah, that's correct. Once it surpasses 6 milliamps of DC leakage, the charge point will sense that, cut the charge off, and stop the connections between the vehicle and the charge point. It will then do an internal reset after monitoring that. Once the user reconnects the charge point to the car, it can then start a charge again, and it will continue monitoring the circuit back up to that 6 milliamp threshold.
Fantastic. So it's really important out there for contractors to really look at the different equipment that's on the market, because if you were just to get a standard socket that that may be allowed for EV charging, and it didn't have that monitoring built in, you would probably have to use the Type B RCD, which would be, you know, a lot more expense for the installation. Okay.
And sorry, Paul, just to mention something very briefly, and just for the guys out there, I did a little viewing of YouTube over the last while to see what was out there again, and I noticed some charge points that don't have DC leakage, the installers are fitting a Type A RCD. That does not meet the regulations that are detailed. And so be clear, guys, just on the requirements and what the charge point has, along with ensuring you're using the right RCD or RCBO. Thanks,
Conor. Yeah, that was in the previous slide there. That's the options. You use a Type B or the Type ARF in conjunction with the DC monitoring. So it's a good point there, Conor. Okay, so as I explained previously, all of our publications cover RCDs in length. This is a table out of On-Site Solutions. It covers the different types of loads that we can see there, and you can see we've highlighted in bold the areas that concern electric vehicle charging. Okay. So a summary, before we go into the questions and things, a summary of why these new requirements are so important. It allows EV charging equipment manufacturers to include electrical safety devices that will protect against electric shock. EV charging installations will be subject to less restrictions, taking account of new techniques and the latest technology. The government targets of 50% EV sales by 2030 will be more attractive, with the removal of these restrictions. It will reduce the potential dangers associated with driving earth electrodes. I briefly mentioned CAT scanning earlier. There's always that concern that you're going to drive through a gas pipe or an electric cable when you put an electrode down, especially a rod. Okay, so we've got less dangers there. Simultaneous contact. If we're using a TT earthing solution, we need to be aware that there's no simultaneous contact with another earthing system. Okay, so if there is simultaneous contact between two earthing facilities, we could have you know, a potential difference and receive a perceived electric shock. So this is going to be reduced if we use these new techniques that are in the charge points. And there's also these solutions, as Conor was explaining, for maximum demand, where we can install these units with confidence, knowing that they will sort themselves out and won't overload the system.